Causal models and linear models are very different. They belong to different realms. The causal models to the realm of the causality demon, and the linear models to the realm of the probability demon. So remember, the causality demon deals with models about reality. It's very simplified models, but they're models about reality. Whereas the probability demon deals with models about populations and samples of values or numbers. So this differentiation is very important to take into account, because typically in psychology we use the linear models or other probability models, not the causal models. Now, with causal models is a relatively new invention, and so we try to create causal models that match the linear models, because we know the linear models better than the causal models. Well, that's not correct. The causal model should come first, because the causal model is a model about reality, and that's what we are interested in science. We are not interested about values. We are interested about reality. So most of the times we can match a linear model to a causal model, but sometimes this is not possible, and we're going to see this later on in the unit. But what happens when there is no match? Well, it's still okay, because the linear model will tell us patterns between values, and which are useful to understand or to know about them. The causal model tells us why those patterns occur. Okay, so let's explain this simple causal model and the equivalent linear model. So in this simple causal model, remember, this is my invention, because the letter C affecting, or the variable C affecting variable Y, the C stands for a constant, so I'm assuming that every observation of this variable will have the same value, and this is typically ignored in causal models. These variables have to take two values or more, cannot take only one value. But remember that I adopt, in this sense, sort of Aristotelian view, in which I want to establish not how y vary among people, but also what is the range of possible values determined by what people have in common. So, for example, if y is a measure of working memory capacity, well, if c is being human, then there is a range of values of working memory capacity that people who are humans, so people, organisms that are humans, will have. So because of our shared genetic components, the genome, we have a possible range of values of y. U here stands for unknown variables. So here we are saying that the variability of y is determined by something that all humans have in common, and other variables which are unknown. So we don't know, and we cannot know those values at this stage. So that's the causal model. Now, as a causal model, it's not a really good one, because it's saying, first of all, the variability of y is determined by a constant. So that doesn't explain much or anything at all. And then the other variable is unknown. So basically, the causal model is not a very good one. Why I'm using these? Well, because I want to show later on a little bit more complex model, and I want to explain the difference between this simple model and a bit more complex one. Now, the linear model that matches this one, there is one way that is most popular notation, which is that variable y is a random variable. Now we are in the probability realm, so we talk about random variables, and it has two components. One component which is the deterministic, so we assign a specific value which we call here beta 0, and then the other part is stochastic, or not deterministic or probabilistic, and that we call epsilon. So the values of y will be the sum of beta 0 plus epsilon. So y being a random variable is, remember, is a trial or an experiment we are going to conduct, and the variable will take one value. But because this is about samples, we are going to repeat that trial or experiment several times, which is equivalent to obtain a sample of participants in psychological studies. And it says that in the value that y takes, in all those repetitions of the trial, the formula will contain beta 0 for all the participants. Now the second part will be different for each participant. So the epsilon will take a different value for the different participants, but as a model we are making a prediction of the range of the possible values. So we say that epsilon is this tilde sign is a means that there is a distribution. So epsilon follows a distribution, and then we say what distribution is that? It's the normal distribution, and that normal distribution has a mean, which is 0, and a standard deviation which we call sigma. Now that sigma, what value we give to sigma? Well, we're going to give a value depending on the sample of values we collect, and we're going to see that later. Now the option 2 is the one that I prefer, but is the least popular. The difference here is that the idea is the same, but instead of putting the stochastic component in the epsilon, or sometimes called error, I put the stochastic component directly into the y variable. So in option 2 it indicates that the random variable y follows a normal distribution with two parameter values, gamma and sigma. And gamma, we are saying that it has a fixed value, which is beta 0, and sigma we are going to estimate from the sample. Now in both cases, in option 1 and option 2, we don't know beta 0 either. So where does beta 0 value come from? Well, we also use the beta 0 that comes from the sample.